So my research is all about providing other researchers mainly with exactly the colour that they need. And we're all very familiar with the fact that if we shine green light and red light onto one spot, it will appear orange, but that's just our perception of the colour. What we see is very different from what we get from the orange component of a rainbow. And my research is all to do with trying to make lasers turn from one colour into another, simply by shining them through a piece of glass. And that's slightly unusual because we expect, if I'm wearing my glasses and I go through traffic lights, if I see a red traffic light, I don't see it as green and just drive through and drive over everybody else through the middle of town. And the way I'd like to describe that is using the analogy of a hill. So here we have a green hill, very steep on one side and not very steep on the other side. And if we have a ball in the bottom of that hill, it takes some energy to move the ball up the hill. But if we do give the ball some energy, we give it a kick, it will oscillate backwards and forwards in here. But if we kick it very hard, it will go a long way up. And now it sees this is very steep and this is quite shallow. And we go for a quick and a slow, and a quick and a slow. When we're dealing with laser light, the ball is an electron inside an atom. And the energy it has looks exactly like this. And we excite the electron using light. If we use very weak light, it just oscillates. And what we get out is the same colour that we put in, the same frequency. But if we kick the ball very hard using a high-power laser light, it again has this asymmetric, very quick, very slow, very quick, very slow. And if we analyse that, that now contains many different frequency components, and all of those different frequency components are different colours.